Today we're going to talk about periodic law and how that applies to different properties of elements, and eventually we'll use that information to talk about how different elements bond together. We know from looking at the properties of groups of elements and of individual elements that the properties of the elements change in a periodic fashion with increasing atomic number. That means that the physical and chemical properties of the elements, to a certain extent, repeat themselves. As the atomic number increases, you move from one row to the next row, then you will see those properties start to repeat. We also know that elements in the same group or in the same family have similar properties. So we've talked about groups like the alkali metals, groups like the halogens, and how all of the elements in those groups have similar properties and characteristics. Today we're going to learn why those elements have similar properties and characteristics, and it has to do with valence electrons. Hopefully you remember from our electron chapter that the valence electrons are all of the electrons in the outermost principal energy level. So you are going to have to remember how to do electron configurations so that you can figure out how many valence electrons a certain element has. When we talk about valence electrons, we talk a lot about this idea that's called a stable octet. Stable usually means that things are kind of in a holding pattern, or that element is not in a very reactive state at that moment. Octet, of course, refers to 8. So a stable octet is where you have a full s orbital and a full p orbital in the outermost principal energy level. And if you count the electrons that you can put in an s, which is 2, the electrons you can put in a p, which is 6, 2 plus 6 is 8. When the s and p orbitals in the outermost energy level are full, then that element has a stable octet. 8 electrons in the outermost principal energy level makes that element be as stable as it can be. An example of that would be like the noble gases. If you look at the configurations for the noble gases, they all, with the exception of helium, end in p6. So that means the s orbital is full and the p orbital is full. Stable octet makes the noble gases very unreactive. This means that all of the rest of the elements will try to achieve a stable octet. In other words, they will try to achieve a noble gas electron configuration. To do that, the other elements either have to lose or gain electrons to try to achieve a stable octet. Depending on whether it's easier or closer to lose or to gain, those elements will either lose or gain electrons to get to that magic number. The magic number is 8. Let's do a couple of examples. We'll start with group 1, all the way on the left-hand side. The first element we'll use as an example is sodium. Hopefully you recognize this isotopic notation. Remember, the mass number is on the top, the atomic number is on the bottom. Let's do the electron configuration for sodium. You should find that there are 11 protons to work with, 12 neutrons to work with, and 11 electrons to work with. So our configuration ends up being 1s2, 2s2, 2p6, 3s1. If you think about how could this element make a stable octet? Well, it has two choices. There's one electron already in the third energy level. If we wanted to make this a stable octet, we would have to add 7 more electrons. That's a lot of electrons to gain. But if we think about the other option, energy level 2 down here is already full. So the other option would be lose this last electron, and then level 2 is the one on the outside and it's already full. So which of those do you think would be easier? Gain 7 or lose 1? The answer, of course, is lose 1. When sodium loses an electron, its configuration becomes 1s2, 2s2, 2p6. And then look at how the stats have changed. The protons are still the same. The neutrons are still the same. The electrons are down 1. So if you're thinking about pluses and minuses, there's 11 pluses and 10 minuses. There's an extra plus here that's not being balanced out with a minus anymore. That extra plus gets written up and smaller over here. That shows that this sodium has lost an electron. There's an extra proton now that's no longer balanced out. That electron configuration then, 1s2, 2s2, 2p6, matches the electron configuration of neon. So sodium then has become a positive ion, and we'll talk about what that means, with a noble gas configuration, and it's positive because it has more protons than electrons now. Time out for vocabulary. What is the word ion? An ion is an atom with a positive or a negative charge. That means it's either lost or gained electrons. You never lose or gain protons when you're talking about ions. We're only talking about losing or gaining electrons. If you change the number of protons, then you change what element you have. That's not what we're doing. We're just changing electrons, which makes the ion either positive or negative. Let's do another example. This time we'll pick one from group 2. Let's choose magnesium. Again, this is our isotopic notation. The mass number is on the top. The atomic number is on the bottom. If we do our stats, we have 12 protons, 12 neutrons, and 12 electrons. The electron configuration would be 1s2, 2s2, 2p6, 3s2. If magnesium wanted to make a noble gas electron configuration, it would need 8 valence electrons. So again, we have two choices. If we wanted this level 3 to be full, to make 8 valence electrons, we'd have to add 6 more. The other choice is to lose these last 2, and then our outermost energy level becomes the second level, which is already full. So which of those choices do you think is easier? Add 6 or lose 2? Of course it is to lose 2. So when magnesium becomes an ion, it loses its last 2 valence electrons, and then its stats look like this. 1s2, 2s2, 2p6, again that's the configuration of neon, 12 protons, 12 neutrons, and 10 electrons. Now there's 2 protons or 2 pluses that are no longer balanced out by minuses. We write those 2 pluses over here, smaller and higher, to show that magnesium has lost 2 electrons. There's 2 protons now that aren't being balanced out. We've again made a positive ion, which has a noble gas electron configuration, and it's positive because there's more protons than there are electrons. Time out for vocabulary. Positive ions go by a special name. We call them cations. This word has the same roots as like the cathode. When you're talking about batteries, batteries have a plus side and a minus side, the cathode and the anode. Same root word for this. Cation is a positively charged ion, such as Mg plus 2. Elements that form cations are metals. Metals are typically the things that lose electrons. But you can also gain electrons, and we'll talk about that in just a second. Here's a couple more examples for you. Everything in group 1, lithium, sodium, potassium, and so on, will lose 1 electron. Everything in group 2, beryllium, magnesium, calcium, and so on, will lose 2 electrons. We're skipping the transition metals again for a moment. If you jump over to group 13 with aluminum, the things in that column tend to lose 3 electrons. So again, it's the metals that make cations and lose electrons. It is also possible to gain electrons, so let's do an example of that. We'll hop over to group 17, which is the halogens, and we'll take fluorine as our example. Look at the stats for fluorine. 9 protons, 10 neutrons, 9 electrons. And here we're just rounding off of the information on the periodic table. Electron configuration would be 1s2, 2s2, 2p5. And you look at your choices. If I want this last energy level to be full, I would only need to add one more electron. If I wanted to drop back to the previous level, I'd have to lose 7, and I still really wouldn't have a stable octet there. So the obvious choice here is for fluorine to gain 1. When it picks up an extra electron, then its stats look like this. 1s2, 2s2, 2p6. Again, it's made the configuration of neon, that's a noble gas. 9 protons still, 10 neutrons still. But now we have 10 electrons. There's an extra negative here that's not being balanced out by a positive anymore. That extra negative gets written over here, higher and smaller, kind of just like an exponent in math, and that shows you that there's an extra electron that's no longer being balanced out. So this time we've made a negative ion, although it still has the noble gas configuration, and it's negative because there's more electrons than protons now. Time out for vocabulary. Negative ions are called anions. Again, that's related to the same word as the anode, like the negative end of the battery. An anion is a negatively charged ion, such as F-. Nonmetals typically form anions, and you could probably guess that. If cations are from metals, anions must be from nonmetals. Okay, let's talk just a little bit about valences. The charge that you write next to the symbol for the element after it's become an ion is called that element's valence. Every element within a column has the same valence. So if we were to go back to that chart you saw a little bit ago that said Li plus, Na plus, K plus, every element in that column has the same charge or the same valence. There is an exception. There's always an exception. Transition metals, the D block elements, are that exception. They can have more than one possible valence. They have some choices in terms of how many electrons they can lose, and it depends very much on the situation and what you're reacting them with. We'll talk more about transition metals in a couple of months, but for right now, we just need to know that they are the exception. They can have more than one possible valence.